thank you all so much for coming, and definitely, if you do need to run up and down the stairs, just do it. I won't be offended. We're going to be talking about something that I am just so excited about, which is applying this new kind of search called vector search. And in this talk, I really want to convince you that, hey, this is a really cool and good thing to do, and can allow you to build some really, really new, interesting search experiences for your users, and B, that it's actually really easy, way easier than you think. We'll start off a little technical, but it will quickly kind of dive into practical details of how you build this. And I hope by the end, you walk away kind of, wow, this is really neat, and this looks like something I can do. We'll have some coding demos. All the stuff I show you, I put it up on GitHub, and I'm easy to reach, and I'll try to share it into the Slack channel for folks. So agenda here, I'll just give you all a quick intro about myself, how did I come to get really interested in vector search? Then I'm going to actually tell you what is vector search, and why is it exciting, what's so cool about it? I think you're going to see pretty quickly, like, wow, this is interesting, and you're going to want to know, how do I actually use this stuff? So I'm going to show you how to use it. And then once you know how to use it, I think there's some really interesting things that start to come out, and I want to show you some of that. I think it'll actually connect nicely to some things that Luke showed you if you were here for the last presentation. So really quickly, I'm the Chief Technology Officer at a company called CaseText. We're a legal research company. That means we build technology for lawyers who have some of the most challenging natural language search needs of all kind of professional verticals. One of the ways that I came into dealing with this concept called vector search, well, we have these users who just desperately need better and better search technology. We built out a system called parallel search that I'll demo for you just really quickly here, because I think it's just such a cool demonstration. So it happened really quickly here, but you can see my user came to my site and they entered this query, and you know, this is lawyer stuff, so it's going to be a little bit technical, but I think it will really stand out to you how amazing it is. So someone asked, is planting a garden sufficient to satisfy the legal requirements of squatters' rights? What we're doing here in the background is using this new technology called vector search to search our database of all US case law, and look at this top search result. I'm not a lawyer, but I can tell you this is actually a quite on-point thing. What's so cool about this is there's basically no keyword overlap between the query that I put in and the result that comes out. Like, the query was planting a garden, the cultivation of land and gardens, and the pasturing of animals, blah, 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 is sufficient to establish the requirements of adverse possession, also known as squatters' rights. Amazing, right? It's a kind of search experience that, until very recently, if folks in the room, how many folks work on search?
Well, yes, we do, but also, could you zoom in on that?
Yes.
Thank you.
We'll make this a little bigger. How many folks work directly with search in their day-to-day in the room here? Just a few. I think you look at that example, and if you've been working in search for a while, getting that kind of search experience to happen is an extremely challenging problem with the technology that existed as of a few years ago. There's been some really, really significant changes in the search space that make search experiences like this possible. So that's what we're going to get into in the talk here. Just really quickly about me. I'm from Lancaster originally. With COVID, I was able to move back. I feel extremely fortunate to be back in Lancaster, and it's just so cool to see how much the kind of tech scene has grown since I've been gone, and just really, really neat. All right, so there is a little bit of math here. Before we get to the good stuff, we have to talk a little bit about what is vector search at a mathematical level. Maybe some of you all took the math tutorial earlier today. I'm not sure if they covered anything about vectors, but I'm going to try to get you up to speed really quick if this isn't something you're super comfortable with. So what's a vector, first of all? Think about a vector as a fixed length array of numbers. If we have two vectors, A and B, so we have two fixed length arrays of numbers, there's a way to measure the similarity between those two vectors. And that measure is called the cosine. And I have a formula here if you want to read through it. But conceptually, we're going to be working in much higher dimensional spaces. But if you think about what's going on in 2 dimensions, well, really, the cosine just gets at the concept of the angle between two vectors, right? So you can see here, this is vector A, this is vector B in the far left-hand corner. These vectors are very similar because they have a very small angle between them. These vectors in the middle picture are perpendicular to each other. And that kind of suggests something sort of special. It suggests completely unrelated. And then you can have this sort of extreme case on the right where the vectors are pointing in the opposite directions, which means something like opposite. And so when you're talking about vector search, the problem you're trying to answer is you've got all these vectors. You want to ask this question. So I've got a vector A in my hand, and I've got this database of all these other vectors. What are the most similar vectors? What vectors have the smallest angle between them among the vectors in my database? Okay, I think that's it for math. Why is that interesting? Who cares? Why should that matter? There's a little bit of an interesting story about some developments that started around 2010. Machine learning people, researchers, they started to get really interested in these kinds of games. And in fact, these are the same games that power GPT, all the kind of very interesting AI stuff that's come out for language in the past that we're hearing more and more about every day. It really started with these guessing games. So the idea is to show the machine learning system a sentence, remove a word, and ask it to guess what word should fill this in. And if it gets it right, gets a point. If it gets it wrong, it gets punished for getting the wrong answer. So you have Lancaster County has more people, or has more blank than people. Make the machine learning system try to guess the word, give it a reward if it does, punish it if it doesn't get it right. And it turns out that playing these games leads into something really interesting. So around 2013, folks started to learn or started to recognize that if you do this a whole bunch of times, you start to get these really interesting ways to represent language data. One of the first big advancements in that area was this system called word2vec that came out at around 2013. And the idea with word2vec is you take a word, and using all of this fancy machine learning stuff, you can map it into a vector of about 300 dimensions. If they're all fixed length, 300-dimensional vector, every word gets a unique 300-dimensional vector associated with it. And there have been more advances since. So there are nice ways to represent longer spans of text, like sentences, for example. And what's cool about these representations is that they capture meaning, semantic meaning, without needing to do some of the things that we've, if you've been doing search for a long time, you've spent a lot of time doing. Building out synonyms lists, building out complex taxonomies. A lot of that stuff gets just kind of blown up by these new approaches. And so then, how do these become search systems? Well, really, now you've got a way to go from a word or a sentence into a vector. If you can put those vectors into a specialized search system, you can build out these amazing new search experiences like the one I showed at the start. Just to kind of make it a little bit more concrete with word2vec, Again, these are 300-dimensional vectors in real life, but just think about them in 2 dimensions. One of the cool things that came out with word2vec is, if you have a word vector that represents king, and a word vector that represents queen, and a word vector that represents man, and one for woman, you can actually do arithmetic to say king minus man plus woman equals queen. And you can do some really interesting, start to do really interesting reasoning with these things. We're not going to think too much about the analogy side of this for this presentation, but the interesting thing for us is really this right-hand side, where in word2vec, the vector for good and the vector for awesome are really close together. And they're distinct and far away in terms of their angle from the vectors for bad and worst, right? And bad and worst are close together. So you can see the yellow vectors are separated from the blue vectors, and within those 2 groups, they're close together. Okay, so how do you get started with building out a system that can take advantage of this in a search context? Well, there's a few steps to this, but basically, you need to take your input text, figure out how do you want to break them up into sentences or paragraphs maybe. Then you take each of those chunks that come out, and you do this process of taking a piece of text and turning it into a vector. So you can think of that as a mapping from a string, right? It's either a sentence, a word, a paragraph, something like that. Turning it into one of these fixed length vector representations. And then you've got your pile of documents that you need to get into your search system. So you run those texts through your segmenter, then run each of those vectors that comes out of the process into a vector storage engine. Okay, so now you've got this big database of vectors. What happens when a user comes and asks a question, like the question at the beginning about squatters' rights? Well, at query time, take the user's query, you apply the vectorizer to it. That maps the input string to the fixed length vector. And then you run that similarity search and you ask, among this huge database of vectors that I have, which vector is the most, which vectors in the database are the most similar? And here's kind of a picture of how that process works in a sort of fully engineered system. Feed documents in. Documents are, it's just a big, you can paste them all together. It's just one big long string. You've got your segmenter that splits that up into, reasonable lengths, like sentences. So you go from string to an array of strings. Then you feed in those strings to your vectorizer, and you get back, a whole bunch of, vectors of dimension, and you shove them into your vector storage system. Similar thing in query time. Run your query through the vectorizer, get back a vector, and then you ask your vector storage, what are the k most similar vectors to the input? And that's how you get to the search results. Any questions? I'm going to show a demo in a second, though, hopefully. That's cool. Yeah?
Just because I'm not sure how the vectorizer works, I noticed good and awesome and bad and worse were kind of all the same angle. Wouldn't they be kind of...
Good question. It's about the relative angle between 2 vectors, right? So what matters in this picture is that the angle between good and awesome is really small, right? So if my user typed in good and awesome have a very small angle between them. Bad and good, actually, if you kind of translate this picture down, I think you should see that good and bad actually have a much bigger angle between them.
So it wouldn't necessarily, because I would expect bad to be completely in the opposite direction of good.
Partly this is a cartoon, and it's hard to picture these things in 2 dimensions, but I think the key thing is really about relative angles between objects.
How does the vectorizer actually work?
Let's get there. Yeah, good question. We'll get there, I promise.
Just to clarify my thinking, but on the right, good and awesome sounding synonyms. So would it be fair to say you have good is the root of the family tree and you're getting the closest relatives to it?
that sounds a lot like the older way of thinking about search, which is, oh, we need to first build out all of these like synonyms lists. What I'm going to show you all in a second is stop thinking that way, because it's much easier.
Just follow up. So what you're saying is the sentence structure around this adding additional context and using that.
I think so. Yeah, I think that's right. All right. Let me show you all a quick kind of demo. And the point of this demo I want to show you is, first, I want to show you that this is really, really cool. So I think you'll walk away with this being really cool. But you're going to see also that I built a full search system in like a pretty small amount of code using tools that are either fully open source or have open source versions or are actually pretty cheap to run at a reasonable scale. So the example I want to work through here is you go to Kaggle and you get all the Star Wars scripts. We're going to take the Star Wars scripts, we're going to split them up into sentences. We're going to put those sentences into a vector search system, and then we're going to ask semantic style questions against the Star Wars scripts. So I'll talk in a few minutes about the different options, but at this point what's cool is there are a lot of different ways to do this. I have one specific way I'm doing it here, but there are other ways now too. I'm going to use this in this example, a project called Weaviate. Weaviate is a fully open source vector search system. Sorry, you all need more. Let me zoom in a little bit. Is that better? Even more. How's that? All right. So we're going to use this system called Weaviate here, fully open source. And someone in the back asked, how do these embeddings really work? We'll get into some details there. There are lots of different ways you can get you can get hold of these vectors. But for now, just to make things easy, we're going to use something that isn't open source, but I'll point you to a version that is open source that you can use. So there's a service called Cohere, competitor to OpenAI. They offer a service where you can put a piece of text in, get a vector back out. And what's, I think, pretty cool about this example, so there's an official, Python, we're using Python here, there are clients in all sorts of languages that you want to work with. There's an official client for this vector search system called Weaviate. So in my example, basically I say, all right, I'm gonna do this. I'm gonna use my Weaviate search system. I'm gonna go, just set up some pretty basic config. Again, this is all code that's posted, so we don't need to walk kind of line through this. But basically, I'm initializing the client. I'm telling it, hey, here's how you're going to get your vectors. This is how you're going to vectorize text. And turn it on. Now, just like in the old sort of search world, you still need to define a schema. So if you're using Elasticsearch, for example, you typically define a data schema. In our case, what we're going to do is lay out a data schema that makes sense for lines from a movie script. So we're going to have some basic metadata type fields, just the title, where the script came from. We'll shove the line number in case that's a useful thing to kind of keep track of what line on episode 4 did this come from. We'll put the speaker in there. Is it Luke or Darth Vader or Chewbacca or whatever? And then the really key part here is just setting up a schema to hold the text, which is the part we're really going to care about for the purposes of this example. And there's some kind of specific config in here, but all it's really telling this system is, hey, we're going to use that fancy Cohere vectorizer that you have an API key for above, and you're going to use that when you see a line from one of the characters. Use that to vectorize the results. I wrote a very simple, very stupid, like processing functions, and these are just these flat TXT files for Star Wars scripts. You could do much better and make this a lot fancier, but basically I'm just reading through, doing that text segmenting step where I split it out into pieces. And then I'm going to load line by line. What's happening right here at the very last line on this block is me. I'm just adding my line objects into that vector search system with that schema that I laid out. So now we get to actually do some searches. I won't run it because it takes like 2, 3, 4 minutes, something like that, to load all that data in. It should already be loaded here. So let's do some searches with this, and we'll start with I think this is actually a pretty cool example. So we're going to run a vector search with the text, "Hey kid, I'm your dad," right? What should we get back? There you go. Look at that. This is really cool, at least to me. Hopefully it's cool to you. The top hit, there's no overlap between the text that came out and the text that went in, but it's exactly on point. It's exactly the line we want for this query. Now the dangerous part, what do you guys want to search for in the Star Wars scripts? Give me a query.
Death Star's operational.
All right, let's try it.
That's a little cool.
Maybe, so I want to give it something hard to do. That's not too bad. It's fixating a little bit on the space station part. This, I think, is pretty solid hit. We didn't quite get the quote we were looking for, but it is still not bad. What's that?
It depends greatly on your point of view.
All right, how do we rephrase that to make it, like, if I just do that, it's going to get it exactly? How can I kind of fuzz that up?
It depends how you look at it.
Good. Let's try that. Let's see if that works. It's sort of not too bad. Like that's pretty on. I wonder if we get it like a little bit later on. Okay, there we go. Fourth hit.
This negotiation is constantly deteriorating.
The last time I gave this talk, somebody asked about the nerf herder line. It didn't do too well. What was this one?
This negotiation is constantly deteriorating.
Yeah, look at that. That's a beautiful top head, right? Deal's getting worse all the time. Was that what you were looking for, or were you looking for something else?
Yeah.
How does it deal with proper nouns? Like if you gave it the name of a planet, or like something similar to the name of a planet?
That's a really good question. What's so cool, and like the internet is full of Star Wars, so it probably knows all the planets because it was trained on the internet. But in a context like the legal context I showed at the beginning, what tends to happen with those proper nouns is this system is so driven by the context around the word, right? So it actually doesn't get too hung up on those specific nouns in most cases because it's inferring meaning from the context around the word, which is similar, I guess, at least for many theories as to how humans actually understand language too. They understand language not by focusing on the specific word, but by the words that are around those words. So playing that missing word game is so important to getting representations that aren't so hung up on like the specific nouns that appear in the system. Very, very different from the old approach to search where you have to kind of engineer around that. So it's challenging. All right. We can do more of those at the end if folks want. But I want to talk a little bit more about how you can. So first of all, what I hope stood out from that demo, it wasn't that much code. There's some boilerplate to work through, but it wasn't hard, right? It was a couple lines, really, a couple blocks in there, probably 100 lines of code, built out a full search system, and look at how fast it was, too. This is impressive stuff. That probably cost, it's like a few dollars a month. That's what I paid for that, at least last month. I think that was my bill. If you don't have a few dollars to spend, how do you do this? There are many options now in this space, and most of the companies here, with the exception of Elastic, are companies, well, obviously in Google. These companies at the bottom are all companies that didn't exist 3 or 4 years ago, I think. On the left-hand side, when it comes to how do you get vectors, the Google BERT, so for whatever reason they called their, it's actually an acronym, but they've used the Sesame Street character to represent this core model that can take a sentence, turn it into a vector. That project is called Google BERT, fully open source, fully pre-trained, although you can customize it yourself. This is something you can run on, reasonably sized hardware. Definitely helps if you have a GPU. If you need to index a lot of documents, vectorizing that can get expensive. But this is something you can realistically host and run yourself. If you don't want to go through all the bother, there are many other companies now that will just do this as a service for you. So the Cohere folks that I used in this example, I don't have any particular attachment to them. It was easy. They offer vectorizing as a service. Same with OpenAI. In the OpenAI terminology, they're called embeddings rather than vectors, but same thing. On the right-hand side, and from the kind of, this is sort of the machine learning side of things, the right-hand side is the software engineering side of things. This space is extremely active. So where can you store these vectors once you have them? Latest versions of Elasticsearch support built-in vector search. Just go, I think since 7, there are some Elastic folks in the room, but I think it's been in there since 7. They're there now. Was it 8?
Yeah, 8.4, I think.
Awesome, yeah. And really, I've used their approach, works beautifulely. And then there's the service I use, Weaviate. There are a few others. Weaviate's fully open source. Pinecone is another big one that people are excited about. This is not an open source project. All right. I just want to talk a little bit about kind of what some of the things that kind of follow or are still challenging and open problems about this. We can go back and look at that demo again in a minute. One thing we didn't play with in there, it turns out that, I've been making fun of the old way to do search, but actually the way you build the best search systems is to combine both keyword and this vector search. If you kind of mix results from both, like there are academic studies that prove this, but it's pretty clear. You'll see it for yourselves. That's the best way to get, that gets you even better results than using either of them separately. What I think is still open there is it's not clear what's the best way to do that. In fact, in that demo I had, you can kind of toggle up and down the mixing ratio for these two things. And so the way you would do this in an application is, I think you really have to tune it for your own domain. So this comes back to some of the more traditional kinds of things you have to do building a search system. You got to experiment, you have to measure stuff, do A/B tests, that sort of thing. I think another and maybe bigger challenge really is it's not, these things are getting pretty good at scaling up. You can handle, 1 million vectors, no problem. Things get a little harder at 100 million and get a lot harder at 1 billion. It's still doable, and these technologies are moving in a direction where that isn't going to be a problem long term, but definitely this would be a challenging approach to take with, say, a logging system, right, where you have a lot of data, most of which is low value. I don't think the scale is quite there yet to support really, really high data use cases like that. But I think it's coming. And the last thing I think that's really exciting here. So what is so, obviously, GPT-4, ChatGPT, these are these technologies right now are just so, they're everywhere, they're hot. And there's a way that vector search and all that generative text technology really go hand in hand. And the way these things go hand in hand is this approach called retrieval augmented generation. And really that's a fancy word for GPT plus vector search. So these models, as hopefully you've all seen at this point, they are writing things at this very kind of human level. And they seem to also be able to do some reasoning on their own. It's really remarkable that that's happening. But you probably also have seen that it can just lie, right? It will just make stuff up. And that's its biggest limitation and challenge. How do you overcome that? The way to overcome that, or probably the most promising way to get it to tell the truth, is to enhance it or augment it with search results from the retrieval system. And in fact, what folks have found is vector search in particular seems to be a key part of getting these GPT-like systems to tell the truth. And you can see this kind of manifested from OpenAI. Their latest thing is this plugin architecture. You may have seen the ChatGPT retrieval plugin. That's an implementation of vector search plus GPT on top. And that really, both kind of on the academic side, there's all kinds of papers now out about this, but basically that's the best tool we have to eliminate those places where it lies. Make it summarize from, make it really cool how you do this, right? You ask that large language model to make queries, right? You just say, hey, tell me how to query this database. You ask it to make a bunch of queries. You then go to your search system and you execute those queries, and then you show it the results and ask it to synthesize and restrict its answering only to that stuff. Yeah. All right. I actually want to make sure we have a little bit of time for questions here. I can show some more demos, but I'd love to hear what folks are interested in from all this.
All right, so we are going to do questions. I've got 2 microphones. I'm going to run them around to you. I see the first person raise their hand down there, so he's going to get the first one. If you have a question at any time, just sort of raise your hand towards me, and I'll get the next microphone to you.
Are vectorizers usually language specific, or do they create a vectorization model that is full of all of these different languages? And I guess second part would be, when they add new languages, do they have to come up with a brand new model?
That's such a good question. Depends on the specific vectorizer. BERT, most of the ones I listed here are actually multilingual to different degrees. It depends a lot on how they were trained. What's, I think, interesting is these models seem to benefit from seeing data from other languages, right? It helps to teach it English and Spanish at the same time. You get better performance on English and Spanish by training together. It's another sort of fascinating emergent thing that's happening with these deep learning models.
Could we see an example of a vector created from a sentence? I'm just curious what that looks like.
Yes. Probably take me a few minutes, but I will. I'll shove it in as an example in one of these workbooks. But yes, it's definitely possible. What it would look like, it wouldn't look very interesting. What it would look like is you get this you take that Luke, I'm your father example, right? If you pass that to a vectorizer, what would come out is a 700 dimensional list of floating point numbers that don't have any meaning to you as a human.
I'm sorry. Oh. Okay. Yeah, So you said that there's like 300 dimensions on those vectors, and that it somehow kind of relates to like synonyms and things.
Yes.
So like, how does it relate those together? I guess.
Yeah, I think that was
Because
what.
I'm familiar with like, I don't know, maybe like one vector, and I compare it to what I typed in, maybe. But like, I don't really understand how the rest of that goes.
You're not alone. It's not a dumb question,
And
and
that's
I
all
don't.
in the vectorization thing.
Yeah, like these. The thing that is really challenging to wrap for people to wrap their heads around with these vector-based approaches is the vectors that come out of this system are not. It's not. You can't look at them and say, "Oh, I get why this is the vector for this thing." They're not interpretable to a human. Where they are interpretable is in this context, where the vector for good and the vector for awesome turns out to have a small angle between them, right? But the individual components in that 300-dimensional vector, they don't mean anything. I'll make sure to print one out in the code here somewhere, just to convince you all that you just won't know what to make of them, right?
Just one question. So I'm just thinking of like different edge cases. So for example, the word with the most multiple meanings in the English language is set. So it's one thing if you have a good and awesome, those are two separate words. But in this case, there's over 430 different connotations for that same word. What are some of the edge cases you've encountered and or limitations of this model?
Great question and a good point. This model will do much, much better if you use the word set in a sentence. If you just give it the single word set as its input, the vector that comes out, you will not recover easily all those synonyms for set. It's really fixed on the context. Now, with the word-to-vec approach, I will say if you, it's too bad I don't have an example running right now, but you would actually see that there's a way to make it spit out synonyms. It would do an okay job at that, but it won't get all 432 meanings of set, right? What is interesting is if you give one of these bigger, sort of sentence-level models the word set in a sentence, it will not get that confused with all the other meanings of set, generally.
So we have time for one more question. I apologize. It's already selected over here. So if anyone else has questions for Ryan, I'm sure he'll be around to catch him after the talk. Go ahead.
So my question here is, you mentioned that this is able to kind of like identify like missing words in sentences. Would this just work for search, or would this also work for generating new sentences?
Yeah, great question. Yeah, so we're focusing on search in this talk, right? But the reason people were playing these word guessing games was much more about generating new text than it was about finding these like cool new representations. It turns out that these representations are a byproduct of trying to get things that generate good text. The point of this BERT model was not to solve vector search. That wasn't the thing it was like trying to do. It was trying to generate, get a bunch of words and generate like the words that follows. It turns out that you can use that, though, to get these cool vectors that have this useful property. Okay. I could stay up here if folks have questions they want to ask separately, and I'm always happy to talk about this stuff. So you can find me on the Amish Tech group. You can email me, and I'll post the examples and the slides into the Lancaster Tech Slack.